Welcome once again. So in this class we will be discussing problems on steam turbines. Specifically, as we discussed in the last class, in this module we will solve problems by graphical method. So here we are solving a problem on single stage impulse turbine. Steam issuing from a nozzle to a D-level turbine with a velocity of 1000 meter per second. The nozzle angle is 20 degree. The mean blade speed is 400 meter per second. The blades are symmetrical. The mass flow rate is 1000 kg per hour. Friction factor is 0.8 and nozzle efficiency is 0.95. So here we have a D-level turbine, which is basically an axial flow impulse turbine. Here he says the steam issues from the nozzle. That means the outlet angle of nozzle is same as the inlet angle for the blade. That is the absolute inlet velocity V1, which is given to be 1000 meter per second. And he says the nozzle angle is 20 degree. We all know nozzle angle means alpha 1 is 20 degree. He also gives us the data, the mean blade speed is 400 meter per second, which is U, right? He also mentions specifically that the blades are symmetrical. That just means the beta 1 and beta 2 are same, they are equal. He has mentioned the mass flow rate to be 1000 kg per hour. Then the friction factor. The friction factor means the loss during the flow over the blades. CB is given to be 0.8, which is VR2 by VR1. Then at last the nozzle efficiency is given to be 0.95. Here we need to calculate the blade angles, the axial thrust, the work done per kg of steam, the power developed by this stage, the efficiency of blades, and at last the efficiency of the total stage. So before we get into the solution part, let me tell you, so basically we need these three parameters for construction of the velocity triangles, that is alpha 1, U and V1. So if these three are given, generally it is considered to be an easy problem. So in this case U, V1 and alpha 1 are given. So let us see how we deal with this problem. So before solving this problem, as I urged you in the last class, please have an understanding and familiarity with the combined velocity triangle for the impulse turbine, which we did use in our derivation. Okay. So based on that, let me start solving this. Generally what we will have U as the base for the both inlet and outlet triangles, right? The combined triangle will have U as the base. So here, before doing that, let me choose the scale here. Since the velocities are of somewhat higher scale, that is one velocity is already 1000 meter per second. So let me take 1 centimeter is equal to 100 meter per second, right? So this is the scale that I choose. That means for every 1 centimeter line that I draw in these triangles, that indicates 100 meter per second velocity in this velocity diagram. So we have a base that is 4 centimeter because, right, U is given to be 400 centimeter. So 400 meter per second. So we have a line of 4 centimeter length, which is U is equal to 4 centimeter, right? Then we also know from this point we will have V1 at an angle alpha 1 and V2 at an angle alpha 2. So from point A we will have alpha 1 and alpha 2 angles, and from point B we will have beta 1 and beta 2 angles, that is VR1 at an angle beta 1 and VR2 at an angle beta 2. So this is the general understanding. If you observe the triangle in the derivation, you will get this. So now what I know alpha 1 and V1. So what I will do, I will have to draw V1 at an angle alpha 1 here. So what I will do, first let me draw an arc for 10 centimeter length, right? Because 1000 meter per second becomes 10 centimeter. So let me draw an arc, and also let me cut this line at an angle 20 degree with the blade speed, right? So from this point let me choose 20 degree which comes up at about this point. So from this point, let me cut that at 20 degree. Okay, if I can cut this, sorry, yeah, this is it. So this is V1 at an angle alpha 1. Alpha 1 is given to be 20 degree. So this is V1 for about 20 centimeter. Now we all know this line joining is known to be VR1 from point B to this point. So let me call this point C. Okay, this line joining will be VR1. Okay, and VF1 will be straight down, that is an axial line from point C. Okay, this should be at right angles. So let me draw this at right angles. So this is my VF1. Okay, so let me join this to complete the inlet velocity triangle. Therefore this is the complete inlet velocity triangle using the given data, which is u v1 and alpha 1. Now after completing the inlet velocity triangle, I did measure the length of VR1, the length of VF1 and the blade inlet angle beta 1, and I have also converted them into velocities based on the scale that I have chosen. Right here VR1 is 6.4 centimeter and thereby it is 640 meter per second. VF1 is measured to be 3 centimeter, so it is 300 meter per second. Right, and beta 1 is measured to be 34 degree, but according to the given data, since the blades are symmetrical, beta 2 also becomes equal to 34 degree. Right, this is the condition. Now this completes the inlet velocity triangle, but what is the data that we know about the outlet velocity triangle? Generally there will be a link given. So in this case that link is actually the CB, the friction factor, which is given to be 0.8, which is VR2 by VR1. We already know VR1. We have measured VR1 to be 640. So since this is 640, VR2 becomes 0.8 into 640, that is 512 meter per second. Right? We know VR2, we know beta 2 also. Now shall we draw VR2 at an angle beta 2? From which point? From point D. Right? So now we will draw from this angle, from this point at an angle beta 2, which is definitely 34 degree. Right? So we will draw a line for about, we will draw 512 meter, that is VR2 is 512 meter per second, therefore it becomes 5.12 centimeter. So I will draw 5.12 centimeter, that is from this point 5.1. So this is the length for VR2 at an angle beta 2. Now from this point I shall join point A, which makes up my V2, that is V2, and also axially downwards I shall draw VF2. Right? So this completes my both inlet and outlet velocity triangles. Now let me measure V2, VF2. Therefore the length of V2 is 2.9 centimeter. That becomes, upon the scale, 290 meter per second velocity, and VF2 is 3 centimeter, that is 300 meter per second velocity. So this is about the calculation based on the triangle drawn. So now let me tell you an interesting thing. So since we have used the formula delta VU1 in our power factor, we all know power P is equal to U into delta VU, isn't it? So before using that, into m by gc. This delta Vu, we need not calculate Vu1 minus Vu2. This we will get directly from the graph, this delta Vu. That is, this delta Vu is the difference between these two apexes. The difference between these two apexes will give us the delta Vu. If we measure this length, we will directly get delta Vu, and also the difference between the vertical difference between these two apexes will give us delta Vf, which helps us calculate the axial thrust. Therefore, now delta Vu is measured to be 9.5 centimeters, which is 950 meter per second, and delta Vf is measured to be 0.7 centimeter, which is equal to 70 meter per second. So this is about the calculation and the graph. Now let us go and calculate what are the parameters that are asked in the problem. The first parameter that is being asked here is the blade angles. Therefore, since we got blade angles directly from the graph, which are measured as 34 degree. Since in this problem, in the de-level turbine, the blades are symmetrical, they are measured to be 34 degree. The second thing that is being asked here is the axial thrust. We already know what is the formula for axial thrust, right? So that is Fa is equal to m by gc into delta Vf. This delta Vf we have directly got from the graph which we have drawn, the velocity triangle. So this is mass flow rate is given to be 0.278 kg per second divided by gc, which is 1000, into delta Vf, which is 70 meter per second. So we will get axial thrust as 0.019 kilonewton. Here if I substitute 1, I will get the answer in newtons. The third thing that they are asking is work done per kg of steam, which is basically the Euler's formula, right? So what is the formula for that? It is W is equal to U into delta Vu by Gc, right? Or we can also write U into delta Vu. So that is 400 into 950. So that becomes 380 kilojoule, okay, per kg. So that is the work done per kg of steam. The fourth thing they are asking is power developed, which is mass flow rate into work done. Power developed, P is equal to m by gc, I will cancel this gc here, m by gc into W, which is U into delta Vu. So we already know that it is 0.278 divided by 1000 into, this is 380 kilojoule. So this becomes 108 kilowatt. So the power developed by this de-level turbine is 108 kilowatt. Now we will come to the important calculation, which is the efficiency of blade, that is blade efficiency, which is the ratio of the work done by the steam to the energy that is given at the inlet. That is efficiency of blade is equal to U into delta Vu, which is the work done by the blade, divided by V1 square by 2. This 2 I will take back to the numerator. So 2 into U into delta Vu divided by V1 square. 2 into U is 400 into delta Vu, we already know it is, we have found it to be 950 divided by V1 square, which is 1000 square. So therefore we get blade efficiency as 77.7%. Now since we know the blade efficiency, we have calculated the blade efficiency, and also the nozzle efficiency is directly given to us in the problem. So a stage consists of a set of blades and a set of nozzle. So thereby calculating stage efficiency is quite easy. That is the multiplication of both blade efficiency and the given nozzle efficiency, that is stage efficiency is equal to blade efficiency into nozzle efficiency, which is 0.95 is the efficiency of the nozzle given into 0.777, which comes to 73.8%. That is the stage efficiency. This is a simple problem on steam turbines based on the graphical method.